All right, I guess we can get started now. Welcome back. It's the 13th lecture of the condensed matter course. When last we left off, we were talking about scattering. The basic experiment is you have some sample, you have a wave at some wave vector k that you send into the sample, and then it's scattered off to some wave vector k prime. And by measuring how much and in what directions you have scattering, you're able to deduce something about what's actually in the sample. A couple of things that we know about these types of scattering experiments. First of all, in order to get scattering from k to k prime, you must have k minus k prime equal a reciprocal lattice vector g. And we derived in the last lecture that that's equivalent to the Bragg condition, 2d sine theta equals n lambda. In other words, since a reciprocal lattice vector is orthogonal to a family of lattice planes, what you're actually getting is diffraction off a diffraction grating with lattice plane spacing d orthogonal to that vector g. The intensity of scattering at any reciprocal lattice vector is proportional to the structure factor of g squared, where the structure factor is the Fourier transform of the scattering potential in the unit cell. So this intensity gives you some amount of information about what's actually in the unit cell. Now, how you actually do this experiment is a little more complicated. There's several methods one can go about. There is the first method, which is the best method, but also the hardest method. Best but hardest, which I'll discuss only very briefly. The best method, but also the hardest method, is to use a single crystal. Single crystal. So single crystals look like this. This is a gorgeous single crystal of sodium chloride, a big single piece of the material without any defects. Now, what you'll find, so you take your single crystal, you put it in the path of your wave, and you look for waves being scattered off of it. What you find is if you take your single crystal, you put it at some arbitrary orientation in front of your beam here. For most orientations, you won't get any scattering at all. In other words, you will not manage to align the families of lattice planes just at the right angle such that the Bragg condition is actually satisfied. So in order to actually get any scattering, what you need to do is to rotate the crystal. Rotate the crystal. Another way to get scattering is to vary the wavelength. Vary lambda. Do one or the other, and then at some angle of the crystal or at some value of the wavelength, you get scattering. You write down in which direction you get the scattering. You measure the intensity of the scattering, and you can deduce a lot of information about the structure factor and therefore about the structure of the crystal. Now, we're not actually going to go into how you analyze such data in any detail in this course, and the reason we're not going to do it is because this method is very rarely used. And the reason it's very rarely used is because it's actually the hardest thing to do. The reason it's hard is because almost without exception, materials don't like to form nice big crystals. Sodium chloride is a suggestion. You have these beautiful big crystals of sodium chloride. Quartz makes nice big crystals. You can probably make a nice big crystal of sugar, something. So there are a couple of materials that you can get to form nice big crystals, but most materials don't. If you cook up some new material in your laboratory or you find some new material in nature, usually it's not crystalline. It doesn't form big crystals. Frequently it's powder. Or even worse than that, you can have what's known as polycrystalline. So this is a picture of a polycrystalline material where you have tiny little crystallites which are about on the size of a micron. So there's a little crystal here, a little crystal here, and those crystals have their axes misoriented with respect to each other, and they're all sort of smushed together. You can think of it as like a powder of tiny little crystals all stuck together. And typically, materials look like this when you make them. It's very, very difficult. It takes a very good chemist and very good material scientist to turn something that looks like this into something that looks like this. So most of the time when one is doing an experiment, one is working with something that looks like this. It's polycrystalline. So to take data on a polycrystalline sample, you use what's known as the Debye-Scherrer method. Debye-Scherrer. Debye is the same guy from the Debye theory of vibrations in solids. Scherrer, someone else, obviously. And the Debye-Scherrer method is also known as powder diffraction. because you can use a powder of the material, lots of tiny, tiny little crystallites in a powder, and you can put that in your sample and get data out of it and actually make sense of it. Now, the general principle of the idea of powder diffraction or doing diffraction on polycrystalline samples is if you're sending a wave into your crystal here, if you imagine for a second you had a big single crystal, and you could rotate that single crystal around, if there was any direction in which you rotated that single crystal and you could get diffraction out at this angle, then somewhere in your powder, somewhere in your polycrystalline sample, the axes will be correctly oriented. In other words, the polycrystalline material, or the powder, represents every possible orientation of the material. So somewhere in your material, you'll have a situation where your family of lattice planes is aligned just in the right way in order to get diffraction from K to K prime. If there's any orientation that will do it, you'll find that crystallite with the right orientation somewhere in your sample. Okay? That's the general principle we're going to live by. Now, if you can get diffraction in this direction with some lattice planes that are sort of lined up parallel this way, you can also imagine that if you lined up your lattice planes this way, you could get diffraction out this way. And in fact, you can imagine rotating those crystallites around the incoming axis, and you'll realize that you can get a whole cone of diffraction outwards. If there's any direction that you can scatter, you can rotate that crystallite around the incoming axis and get a cone of outgoing waves. So the way the experiment actually looks in a setup is kind of like this. There's an incident X-ray beam, there's a polycrystalline or powdered specimen here, and then you get these cones of outgoing waves, which you then try to measure. Remember that it's marked here, so you don't forget. The total deflection angle is 2 theta, very important, common source of error. And 2 theta can go anywhere from 0, meaning it's not scattered at all, to 180 degrees, meaning it's directly backscattered. Now, the way one used to measure it is you would take this sort of round environment and you would line the inside with photographic paper, and you would just expose the photographic paper to the X-rays, and you would see these nice conical signals coming out for these various different cones coming out like this from your polycrystalline sample. But in modern days, photographic paper is not used. It's much more convenient and actually much more accurate and much more sensitive to use semiconductor detectors. So it's usually what you actually get out of your experiment now is a plot that looks like this, where what's plotted across the bottom is the scattering angle and the intensity vertically. So you'll see there's a peak here at 20-something degrees, another peak at 30-something degrees, which might correspond to this ring and then that ring, and so forth. And this is the kind of data that we're going to spend our time analyzing. Okay? So this is sort of a classic type of question for exams: analyze a powder diffraction pattern with the Debye-Scherrer method. So there's a couple rules for following this method. So I'll write them down. It's fairly difficult to find a book that explains this well. I think it's explained well in my book, but if you don't like the explanation in my book, you're kind of out of luck because there aren't a lot of other books that explain it. So sorry about that, but that's just how it is. So rule number 0 is know the wavelength. Know your wavelength lambda. Why do you know your wavelength lambda? Well, you're the experimentalist. You put in the X-ray beam. You had the X-ray apparatus, so you know presumably what the wavelength of the X-ray is. So it's a good thing to start with. Know your wavelength. Probably know it pretty accurately, actually, if you're a good experimentalist. Step 1, measure the angles. Measure angles. Angle of scattering, which is 2 theta, not theta. Remember that. It's going to be important. So here's some data we're actually going to analyze where they've done the first 2 steps. This is aluminum. They're doing scattering off of, or aluminium, I guess, in this country. And the wavelength is known extremely precisely in this setup. This is done with a typical X-ray tube, and they have 6 digits of precision as to how precisely they know the wavelength. Remember, the reason they know their wavelength so precisely is because this is an electronic transition between 2 eigenstates in an atom. It's an electron falling down from one eigenstate to another eigenstate, so the energies of those eigenstates are very, very precisely defined. So you know the wavelength with very high precision. Then you get this data, all these peaks, as a function of scattering angle 2 theta, And fortunately, in this particular picture, they've actually measured the angles for us, 38.43 degrees, 44.67 degrees, and so forth. And I've also labeled the peaks with letters so we can keep track of them: peak A, peak B, peak C, and so forth. Just one hint that if you're ever given a powder diffraction pattern and you have to measure the angles yourself, it will really help a lot if you get the angles very precise. If you get the angles off by a little bit, you can get very confused. It won't be obvious what the result is supposed to be. So try to measure it as precisely as you can. Okay, for each scattering angle you measure, step 2, angle. So step 2 is calculate the lattice plane spacing. So lattice plane spacing, using Bragg's law, and that is d equals lambda over 2 sine theta. Okay, so for each scattering angle you see, that's representing a family of lattice planes with a spacing d equals lambda over 2 sine theta. Now you might think it should be n lambda over 2 sine theta, but in fact you don't need the n up here because the higher values of n will correspond to different thetas that you will also measure. So you'll just be overcounting if you put an n upstairs. So you just need to keep lambda over 2 sine theta. Each angle corresponds to one lattice plane spacing. Okay? All right. So step 3, so this is for us. This is sort of not in the real world. We can assume cubic of some sort. Assume cubic. It's actually not a bad assumption in the real world, too, meaning simple cubic, simple BCC, or FCC. I have never seen, in 25 years of exams, I have never seen a third-year exam that has asked you to figure out a powder diffraction pattern for anything more complicated than simple cubic, BCC, or FCC. Those are the only lattices you'll run into on your third-year exam. That's almost a promise. I mean, of course, they could do something for the first time, but it's pretty good assumption that this is all you're ever going to run into. In the real world, you'll run into things that are more complicated, but it's not a bad thing to start with this as an assumption, and if you can't get the data to fit these, then you go on to more complicated possibilities. All right, assuming cubic, we also have, we'll remember that the lattice plane spacing, this is something we derived, corresponding to Miller indices HKL, is the lattice constant A divided by the square root of h squared plus k squared plus L squared. It's something we derived, I think, in the last lecture, or maybe the one before. So what does that give us? That gives us that a squared over d squared is h squared plus k squared plus L squared. Now, we don't know what a is yet. We're going to try to figure it out. But we know a bunch of d's. So what is this going to tell us? The ratio of d's are going to be, these h, k's, and l's are integers. So the ratio of 1 over d squareds are going to be in integer ratios. Okay? So we're going to declare this thing, this quantity, h squared plus k squared plus L squared. We're going to call it n. And let's see what we're up to. We're up to step 4. We're going to look for integer ratios. Ratios of n. And then once we have the integer ratios of n, we will look for selection rules. Look for selection rules. Rules. Okay, so let's recall from the last lecture what the selection rules were. Given h, k, and l, if we had a simple cubic lattice, all h, k, and l are allowed. All h, k, and l correspond to reciprocal lattice vectors for the simple cubic lattice, so these are all allowed. For a BCC lattice, we derive the selection rule that h plus k plus l must be even. For an FCC lattice, we derive the selection rule that h, k, l all even or all odd. So we can actually start making a table of the possibilities. Actually, maybe I'll put the table over here. So over first column, we'll put h, k, and l. This is the possible families of lattice planes. We'll write the number n, which is h squared plus k squared plus L squared. And then we'll write simple cubic, BCC, and FCC, and ask whether they're allowed. So what's the simplest possible family of lattice planes we could be talking about? We could be talking about 1, 0, 0. So n, h squared plus k squared plus L squared is 1. Simple cubic, yes, that's allowed for simple cubic. All h squared plus k, all h, k, and L are allowed for simple cubic. BCC, it's not allowed because 1 plus 0 is odd, so this is no. FCC is not allowed because they're not all odd or all even, so it's not allowed for FCC. How about the next simplest one, 1, 1, 0. H squared plus k squared plus L squared is 2. Simple cubic, well, yes, that's also allowed. BCC, well, 1 plus 1 plus 0 is even. 1 plus 1 plus 0 is 2, so that's allowed, yes. FCC is not allowed because they're not all odd or all even. 1, 1, 1. H squared plus k squared plus L squared is 3. It's allowed for simple cubic. For BCC, it's not allowed because the sum is odd, but it is allowed for FCC because they're all odd. Then 2, 0, 0. Keep going. So 2 squared plus 0 plus 0 squared is 4. It's allowed for simple cubic. The sum is even, so it's allowed here. And they're all even, so it's allowed here. And you can make up a big table of these things. It's worth doing to keep track of which Miller indices you should observe for which possible lattice type. Now, from this type of table, you can make a list of the possible integers n that you would see for the different lattice types. So for simple cubic, you get n, the possible n's you get are 1, 2, 3, 4, 5, 6, 8. So what happened to 7? So all the possible h, k's, and l's are allowed, but you'll discover if you try, there's no h, k, and l that if you square them and take h squared plus k squared plus L squared, you'll get 7. You just can't find integers. It's sort of a number theory type of result that you just can't find 3 integers that when squared and added together give you 7. So 7 is missing, and so forth. And I think the next one that's missing is 15. For BCC, n is 2, 4, 6, 8, so forth and so on. I think the first one that's missing is 28, actually. FCC is the most interesting one. FCC, the series is n equals 3, 4, 8, 11, 12, 16, and so forth. Actually, I think I wrote these all down already. Yeah, it's on this slide. So here's exactly building that whole table again. We wrote down the first 4 elements of this table. Here's the n's, h squared plus k squared plus L squared, 1, 2, 3, 4, 5, 6. When you get to 7, there's no set of Miller indices that when squared and added together gives you 7. And you look at FCC and the possible Miller indices that are allowed for FCC. The first one is 1, 1, 1. Those are all odd. That gives you a total n of 3. The next one that's allowed is 2, 0, 0. Those are all even. That gives you 2 squared plus 0 squared is 4. That's allowed. The next one that's allowed is 2, 2, 0, all even. 2 squared plus 0 squared is 8. The next one that's allowed is 3, 1, 1, all odd. That gives you 11, and so forth. So these are the series that we want to look for. So actually, let's do that for this aluminum data. Oh, and here's the series written out: 1, 2, 3, 4, 5, 6, 8, 9, missing 7, 15, and 23. All even integers excluding 28, 60, and so forth. Actually, it's not a coincidence that 28 happens to be 4 times 7, and 60 happens to be 4 times 15. You can convince yourself why that's true. And then FCC is 3, 4, 8, 11, 12, and so forth. OK, so here's the data again. Let's go through this procedure, all the steps one by one. So here we measured all of the angles, or someone measured it for us here. It was very nice of them. Here, so we make a table of all these angles. We calculate d equals lambda over 2 sine theta. So here's d lambda over 2 sine theta for all of these scattering peaks. Then we have this statement that 1 over a squared over d squared is h squared plus k squared plus L squared. And we want to find integer ratios of 1 over d squared. So how do we do that? Well, let's declare this number here, 2.3405 angstroms. We'll call that d sub a. And we'll make a table of d sub a squared over d squared, where d is all of these possible values of d. So the first slot is, by definition, 1. 2.3 squared over 2.3 squared is 1. But the second one, 2.3 squared over 2.02 squared, is 1.33, and so forth and so on. We get this in this table here. Those aren't integers, but they're pretty close to integers. If you multiply them by 3, you get a set of things that are really, really close to integers. And you'll see that that pattern is really 3, 4, 8, 11, 12, 16, 19, 20, which is the FCC series, 3, 4, 8, 11, 12, 16, 19, 20. So we've concluded from this that the aluminum scattering pattern we found corresponds to an FCC lattice. We can actually go on a little bit further to calculate lattice constant. So this might be step 5. Calculate lattice constant, or the size of the unit cell, constant A, which would be D times the square root of k squared plus L squared plus h squared. Oops, I did that in the wrong order. H squared plus k squared plus L squared usually. All right, same thing. And if we do that, there are the Miller indices written down for the peaks, and here's the A's. And they're all pretty close to the same, to about 3 or 4 digits. They're not exactly the same, so there's probably some error in the measurement of the angles, or something like that has gone wrong. But to within 4 digits of accuracy, we've measured the lattice constant A for aluminum. Okay? So that's generally how it works. Now, when you get good at this, you don't even have to really do this whole calculation. You can sort of look at the pattern and have a pretty good idea what it is. So this, there's aluminum there. There's the Miller indices labeled appropriately. So I'm going to show you a pattern, and without actually doing any calculation, we can tell what the lattice type is. Now, there's only 3 possibilities. If you give me a reason, just give me a reason. Simple cubic. What's the reason?
No 7.
Very good. All right. So that's so no 7. So that one's yours. So you can see here that the first peak, so that the spacing of the peaks is not completely uniform, and that's because of the sine theta factor. That sine theta sort of spaces things out more when you're at low angles than it is at high angles. But you can kind of see that the spacing from 1 to 2 isn't so different from 2 to 3, 3 to 4, 4 to 5, 5 to 6. But then there's a hole where 7 is supposed to be. And then 8 to 9, 10, 11, 12. And you see actually there's a hole where 15 is supposed to be. And if you go all the way up to 23, you'll notice there's a hole where 23 is supposed to be. And that's the series that you expect for a simple cubic. So you can just look at this scattering pattern for barium titanate and know that barium titanate is a simple cubic lattice. Okay? That's how it works. Pretty cool. All right. Incidentally, barium titanate is a fairly important material for the optoelectronics industry. It's used for various things. Now, there's more information in this. There's more information in this scattering pattern than we've used so far. All we've used is the angles of scattering. We haven't used anything about the intensity of scattering. And there's a lot of information in the intensity of scattering that we can make use of. So let's see if we can understand how much scattering we should get for Miller indices H, K, and L. Well, first of all, there's the structure factor, S of H, K, and L, which gets squared. Now, all right, let's even write it out. So the structure factor, remember, there's S equals S lattice times S basis. And S lattice does nothing more than enforce selection rules. Enforce selection rules. So we've done that, so that's not going to be interesting for us. S basis, well, there's only one atom in this basis because it's just one type of atom, a single atom in the basis. It's just a pure FCC lattice with no interesting basis. So all you get is the form factor for aluminum. And this form factor for aluminum decays with increasing G, as we mentioned last time, or increasing angle, or increased theta. So we expect that the total scattering is going to drop slowly as a function of increased scattering angle. But that's not all that contributes to the intensity. There's 2 other factors which contribute to the intensity. The first is the probability of alignment. So this is the probability that a crystallite will align in just the right way in order to get scattering. We'll come back to that in a moment. And the last factor is known as the Lorentz factor, Lorentz, or sometimes Lorentz polarization factor, which is really a geometric factor. We're not going to say too much about it, but I'll show you what it looks like. So this function is a function which actually, it varies fairly rapidly as a function of angle, but then when you're at intermediate angles, it's fairly flat between around 60 and 140, and then it goes back up eventually at around 140. It starts going back up. It's the Lorentz polarization factor. It's really a feature of how you set up your experiment. And so if you're an experimentalist, you will know what this factor is in advance before you do any sort of measurement. Now there's a sort of a glitch here, which is that sometimes when people present you with X-ray patterns like this one, they'll have already divided by the Lorentz polarization factor here, and other times they will not have divided by the Lorentz polarization factor. So really, if someone shows you data like this, you should ask, is that raw data, or have you divided out by this Lorentz polarization factor already? And embarrassingly enough, on many exams, they'll ask you a question, and they won't tell you whether they've divided by this or not. So if you want to be safe, you should say, you should have told me whether you divided by this factor or not. I'm assuming whatever. So anyway, so that's this factor. And it also, for most angles, so here we're only scattering up to about 120 degrees here. So this factor here is decaying as a function of angle up to 120 degrees. This factor here is also decaying as a function of angle. So we'd sort of naively guess that we should always decay as a function of angle as you increase the angle. And more or less, the scattering amplitude is decaying as a function of angle. But we haven't looked at this piece here, probability of alignment. Well, you might think to yourself, all the crystallites are aligned completely randomly, so that factor should be trivial. It should just be 1. But think about this for a second. You'll remember when we talked about families of lattice planes, if we're thinking about a lattice plane spacing which is associated with the 1, 1, 1 family of lattice planes, it could have been the 1, 1, 1 family of lattice planes, or the 1, 1 bar 1, or the 1 bar 1, 1, or the 1 bar 1 bar 1. There's 8 possibilities which would all give you exactly the same lattice plane spacing that you could scatter off of. So in fact, this probability of alignment is actually the multiplicity of HKL. So if we go back to this table here, let's see, add the multiplicities onto this table. If we're thinking about the 1, 0, 0 Miller indices, there's 6 possible directions which would present the same lattice plane spacing as 1, 0, 0, the 6 possible axes of the cube. But if we're looking at the 1, 1, 0, there would be 12 different ways you could face the cube that you would present the same lattice plane spacing. And someone won a chocolate bar for realizing that 3, 2, 1 has a multiplicity of 48. So these are the factors that we want to keep track of if we want to understand the intensity of the scattering. Now, let's look at this. Let's look at 2 peaks that are actually fairly close to each other in angle. Why do I want to look at 2 things that are fairly close to each other in angle? Well, if you both F and L are decaying kind of slowly as a function of angle. So here, if we take angles somewhere in the middle, around 100, 120, then this thing is pretty flat. This thing is decaying only slowly, and we can only worry about the multiplicity. So let's take these 2 peaks here, 311 and 222. 311 and 222, they have these F's and L's in them, but F and L are pretty much the same because we're scattering at about the same angle for 311 and 222, just a slight difference in the angle. But the multiplicities, let's back up to the multiplicities here. 311 has a, 311 has a multiplicity of 24, where 222 has a multiplicity of 8. So we would guess that the peak for 311 should be 3 times higher than the peak for 8. And indeed, the peak for 311 is pretty close to 3 times higher than the peak for 222. Okay? So that's how the multiplicities get in the game as well. Okay? So these intensities of scattering can actually be very useful for analyzing data as well. I'm going to show you a sort of artificial example of where this might be useful. So here is some fairly bad data for taken on iron. Now, it's bad for a couple reasons. The first reason is because the peaks are pretty broad. The second reason is because you only see 3 peaks. With 3 peaks, it's pretty hard to tell which series you're talking about here. You can't count out to the 7th and see if the 7th is missing because you only have 3 peaks. So this is going to be a little bit difficult, but we have the amplitudes of the scattering, and that actually might be helpful. So we'll see if we can make use of that. So we go through the same exercise of measuring the angles, calculate the lattice plane spacing, take the ratio of the first lattice plane spacing to the various lattice plane spacing, dA 2.03 squared over 1.4 squared is 2, 2.03 squared over 1.17 squared is about 3. We realize those are in the integer ratios of 1, 2, and 3. So those could be 2 possibilities. Either it's simple cubic, and then these scattering peaks correspond to 1, 0, 0, 1, 1, 0, and 1, 1, 1, meaning this integer n, h squared plus k squared plus l squared is 1, 2, or 3. Or it could be n is 2, 4, and 6. Those would still be in the ratio of 1, 2, and 3, but they would correspond to Miller indices of 1, 1, 0, 2, 0, 0, and 2, 1, 1, which, when squared and added up, give you 2, 4, and 6. So we don't know which one it is just by looking at this data. So what do we do? Well, there's a couple of approaches we could take. One approach is that we could try calculating the lattice constant, A. So if we calculate the lattice, we could assume simple cubic, calculate the lattice constant, and we would get D times square root of h squared plus k squared plus l squared gives us 2.03 angstroms. If we did the same thing for BCC, we'd get something that's square root of 2 bigger because we're multiplying all the n's by 2. So this thing inside the square root is multiplied by 2 overall. So instead of getting 2.03, we get 2.86. Okay? So we have a different lattice plane, a different size of the unit cell, the conventional unit cell for a BCC case. Now, why does that help us? Because we don't know what the lattice constant is for iron. But it does help us because we could try calculating the atomic density. For the simple cubic case, we would have 1 atom per 2.03 angstroms cubed, whereas for a BCC, it's 2 atoms in the conventional unit cell per 2.86 angstroms cubed. And those densities differ from each other by a factor of square root of 2. So if we knew the atomic density of iron, we could tell which one it is. So we'd be done. But suppose we don't happen to know the atomic density of iron. So what do we do then? Okay, there are other things we could invoke. We could look at the scattering amplitudes, which was what I was leading up to. Now remember, so at this scattering angle, the Lorentz factor is decreasing. The form factor is always decreasing as a function of increased angle. So you would sort of naively expect that A should be bigger than B should be bigger than C. But it's not. C is bigger. The only thing that could possibly explain that is if the multiplicity of the peak C is bigger than the multiplicity of B. So if you look at the simple cubic, we identify the first peak as 1, 0, 0, the second peak as 1, 1, 0, and the third peak as 1, 1, 1. The multiplicity of B is bigger than the multiplicity of C, so there's no reason you would ever get the C peak to be bigger than the B peak. However, for BCC, the multiplicity of the C peak, 2, 1, 1, is 24, whereas the multiplicity of the B peak is 2, 0, 0, so C should actually be bigger than B. Now, if you just look at the multiplicities, you would expect a factor of 4, that C should be 4 times bigger than B, and it's not 4 times bigger than B. It's only about 2, maybe 2 and a bit times bigger than B. But the reason it's not a full 4 times bigger is because F is dropping, the form factor is dropping, and the Lorentz factor is dropping also at the same time. So it's competing with this decreasing effect from these other 2 terms. But at any rate, just by looking at this data, we can tell just from the amplitudes that this must be BCC. Of course, we also know that iron is not simple cubic because there's only one element that takes a simple cubic lattice, and that's polonium, and iron isn't polonium, and so that does it also. It's sort of a cheating way to go about it. All right, so let's do one more example. This is the example of neutron scattering. Neutron scattering is very similar to X-ray scattering, but it's a little simpler because the form factor is just a constant. It's just the nuclear scattering length. It's not a function of G. So what's the lattice type? Oh, my gosh. Sorry. Yes. I'm not so good at this. So yes, so you can tell it's FC. This is FCC without doing any calculation. because of the pattern that you can sort of imagine that if this is 3, this is 4, then there's a big spacing to 8, then a little spacing to 11, 12 close together. So you can kind of see that the spacing is the right spacing for an FCC lattice. Okay, so but if you wanted to go through the whole story, we can go through the whole story carefully, measure the angles, calculate the lattice plane spacings, take the ratios of the 1 over the square of the lattice plane spacings. You get 1, 1.3, 2.6. We realize multiplies these by 3. We realize these are integer ratios. 3, 4, pretty close to 8, pretty close to 11. Actually, the data isn't so great. And if you back up, well, you'll realize that these peaks are pretty broad. They're not really that accurately, resolved. It's not the greatest data. This was data taken in 1959. I mean, modern data is much better. But okay, you can definitely see that it's going to be FCC. And you can also label the Miller indices and get an estimate of the lattice constant. Okay, so the lattice constant, maybe you don't know it within a few percent, but you have a pretty good estimate of what it is. But in fact, what we have here, and we can write out the multiplicities, we can label the peaks as well. Actually, you'll notice that by doing this, you'll notice that you would have predicted a slight peak here, a 420 peak here, where the shoulder is. It's not there. I mean, but if you kind of look at it carefully, you see that there's kind of a weak shoulder. You can sort of imagine that it's just a very small peak that's sitting there. Now, so this tells us where the peaks are, but there's more information that we would like to get. We would like to know what the basis is. So we know that titanium carbide is FCC, and it has to have a basis that has 2 elements in it, with a basis of 2 atoms. And we'd like to know what is the form of the basis. In other words, where do you put the titanium, where do you put the carbon in the unit cell? So can we figure that out? Well, okay, so arbitrarily we can always assign titanium to the position at position 0, 0, 0 in the unit cell. We'll just define the titanium position to be 0, 0, 0, but then carbon we'll put at position UVW, which we don't know. Incidentally, I should have mentioned titanium carbide is actually a really important material. Does anyone know? Here's another one. Does anyone know why titanium carbide is really important?
They use it for brake discs.
Use it for what?
Brake discs?
Yeah. Anything that needs to be really hard. Okay, yeah. So titanium carbide is one of the hardest materials out there, short of diamond. I think there's only 1 or 2 others that are as hard as titanium carbide. It's easy to it's easier to make titanium carbide. It's not as expensive as diamond. So whenever you need anything that needs to be very tough, it's very frequently used for things like tools. If you need a saw or a drill bit that's going to cut through something very hard, it's very frequently titanium carbide. So that's why they did this experiment way back in 1959, because it was an interesting material even back in 1959, and they didn't even know its structure. So, okay, so I think they did. Maybe they did know the structure from something else. I'm not sure, but I don't think they knew it. So at any rate, we don't know where the carbon is in the unit cell. So we're going to see if we can use this intensity data from these peaks to figure out where in the unit cell it is. So generally, the piece we're going to be interested in is the basis structure factor, which ends up getting squared. And that is, well, maybe I'll write this out here first. S basis equals sum over alpha in the unit cell, e to the I g dot r alpha times b alpha for the 2 atoms in the unit cell. So S basis squared here will be B titanium plus B carbon, we'll write it as e to the 2 pi I HKL dotted into UVW. And then you take that thing and you square it, and that will give you the basis structure factor. Now, if you knew what these nuclear scattering lengths were, B titanium and B carbon, you might have a fighting chance of figuring out what UV and W were. But suppose we didn't know that. Can we still make any progress? Well, we can make a little bit of progress if I give you a hint. This is the kind of hint you get on an exam. The kind of hint you get on an exam is that FCC with 2 atom basis, there's only 2 common ones. Only two common ones, common possibilities. In fact, I don't even know of any cases that are not one of these two. There may be even a theorem that you can't have anything else. I'm not sure about that, so don't quote me. But anyway, the two possibilities, we've seen them both before. There's a so-called zinc blende structure, which is the same as the gallium arsenide structure, which we talked about in class, which puts UVW at the position 1 quarter, 1 quarter, 1 quarter. And the other possibility we also discussed is the sodium chloride structure, which has UVW at 1/2, 1/2, 1/2. So can we figure out which one of these two possibilities it is? Okay, well, let's see if we can do it. So let's first try zinc blende structure. Okay, so in this case, S basis squared equals, well, we have B titanium plus B carbon e to the 2 pi I HKL, and then 1 quarter, 1 quarter, 1 quarter, which we can also write, this factor here, this exponential factor here, is also equivalent to e to the pi over 2 times I times H plus K plus L. Or equivalently, this would be I to the H plus K plus L. So, okay, I'm out of room here. Move over here. So we have S basis squared equals B titanium plus B carbon times I to the H plus K plus L squared. Okay, and what is that as a function of H, K, and L? Well, there's three possibilities. Case 1, or maybe case A, is that H plus K plus L is a multiple of 4, equals 4 times an integer n. So in that case, we get S basis squared equals B titanium plus B carbon absolute value squared. The second possibility, case B, is H plus K plus L is still even, but it's not a multiple of 4. So we'll call 4n plus 2, in which case we get S basis squared equals B titanium minus B carbon squared. And the third case, case C, is H plus K plus L is odd, in which case S basis squared is B titanium plus or minus I times B carbon squared, which is B titanium squared plus B carbon squared. Good? All right. So let's stare at that for a second. And what can you conclude from this? Well, no matter what B titanium and B carbon are, as long as they're real, which they are, the largest of the three possibilities is always either case A or case B. If B titanium and B carbon have the same sign, then case A is the largest of the three possibilities. If they have opposite sign, then case B is the largest of the three possibilities. So the largest peaks should definitely have even H plus K plus L. Now let's look at this data, and you'll see H plus K plus L. And you'll notice that the highest peaks always have odd H plus K plus L. Systematically, always. So 111 is high, 311 is high, 331 is high, 333 is high. All the other ones are small, are even. So this does not agree with the data. Does not agree. Not agree. Well, we can try something else. We can try the sodium chloride structure. So try sodium chloride. In which case, we have, well, I wrote it over here somewhere. Yep, over there. It's 1/2, 1/2, 1/2. So S basis squared is then B titanium plus B carbon times e to the 2 pi I H K L dotted into 1/2, 1/2, 1/2, and then all squared. And that we can rewrite as B titanium plus B carbon times minus 1 to the H plus K plus L, all squared. So there's two cases we can have. Case 1, case A is H plus K plus L is odd, in which case we have B titanium minus B carbon squared is the answer. Whereas case B is H plus K plus L equals even, in which case we have B titanium plus B carbon squared. Okay, so now which one is largest here? Well, you can see that if B titanium and B carbon have the same sign, then the even will always be larger, whereas if they have the opposite sign, then the odd will have larger. Well, if you look at the data, the H plus K plus L odd is clearly much larger, and so that tells us it's consistent with this case, that if B titanium has opposite sign of B carbon. So the large peaks are B titanium minus B carbon squared, with B titanium and B carbon having opposite sign, and the small peaks are the sum of the two with them having opposite sign as well. Okay? Everyone happy with that? More or less? A little bit? Yes, please say yes. All right, thank you. All right, good. So let's see. So yeah, there's the summary slide. So we conclude it has to be sodium chloride structure. Let's see. So we can actually go on and discuss, let's discuss how you make neutrons for a second. So we discussed how you make S-trays in the last lecture, I think, but we haven't discussed how you make neutrons. This is a neutron facility, a spallation neutron source, also right down the road next to the synchrotron source, rather large and expensive apparatus. But what we need is neutrons with a wavelength on the order of 1 angstrom. How do we get that? Well, if the wavelength is 1 angstrom, the momentum is 2 pi h bar over lambda. And from that, we can calculate that the energy we need is p squared over 2m equals approximately 80 millielectron volts, or about 800 Kelvin, if you put in the appropriate factor of Boltzmann's constant to make it into a temperature. And this might sound to you like it's hot, but in fact, 800 Kelvin is really, really cold for neutrons. Why is that? Well, how do you get the neutrons in the first place? Making neutrons. Well, back in the old days, they didn't have neutrons. And then along came the Second World War and the atomic bomb project. And after the atomic bomb project, they had nuclear reactors. And nuclear reactors have neutrons as a byproduct. So possibility 1 is byproduct of fission. And you can imagine that when a neutron comes off of a nucleus in some fission process, it's coming out with millions of electron volts rather than millielectron volts. So it's extremely, extremely energetic. So this 800 Kelvin is extremely low energy. There's a more favored method for making, because people don't like to have atomic reactors in their backyard these days, there's a more favored method for making neutrons. And in fact, it's a more efficient method as well, which is known as spallation. And that's what this source is. This neutron source is a spallation source. The idea of a spallation source is not unlike the idea of an X-ray tube, where you take usually a proton, and you accelerate it to about a giga electron volt, and you hit it onto a target, and the idea is to smash some nuclei, and kick off some neutrons. Now again, since you're hitting it with such a high energy, you're going to kick off neutrons with some very, very high energy as well. So whichever method you use to create neutrons, they're coming off with an incredibly high energy, and you have to make them cold. So to make them cold, what you use is you use a moderator. And a moderator is basically just a big tank of some substance where the neutrons can go in the substance and bounce around, giving off their energy to the substance. So frequently people use carbon, graphite is carbon, graphite, carbon, water, heavy water, lots of materials, anything that the neutrons can bump into and give off their energy to. And eventually, at the other end of this thing, you get neutrons, and you want to cool them down until they have about 800 Kelvin worth of energy. Now, once you have the neutrons coming out, you need to somehow figure out how to make them monochromatic. Monochromate, meaning you just want to get one wavelength. Remember, that was the first rule, know your wavelength. So you have to monochromate. So how do you monochromate? One way, method one, is to diffract. So you can use a crystal that's known. We mentioned this in the case of X-rays as well. Diffract from a known crystal, And that sometimes works, but there's another method which is also used, which is very nice for neutrons, which is a time of flight method. Time of flight, which works in the following way. So you have a beam of neutrons coming in over here, and then you have sort of a window which you can open and close. Open and close whenever you want. And then you have a long spacing L from here to here, and another window which you can open and close. So you open up and close the window very quickly to let in a little pulse of neutrons, and then at some time delta t later, you open up the other window. So then you know L, you know t, so if it made it from the first window to the second window in delta t, you know its velocity. So L divided by delta t is its velocity. If you know its velocity, you know its momentum. If you know its momentum, you know its wavelength. So you can select by giving it a certain amount of time to get from the first window to the second window, you can select for a particular velocity, therefore a particular momentum, therefore a particular wavelength. One more thing that I do want to mention about neutrons, we'll say maybe just one or two more things about them in the next lecture, but I do want to mention now, is one of the reasons people like neutrons is the neutrons actually have a spin. And that enables you to see things that have importance, where the spin is important. If you have more spins in one region than another region, the neutrons are sensitive to that. They feel the local magnetic environment as a potential, whereas photons do not. They don't care about the local magnetic environment. Neutrons do, because the neutrons have some spin. Okay, we'll stop there and we'll pick up, finish this off next lecture.